Welcome everyone to this video. I am Mr. Ish. I hope everyone's doing well. We are solving the second order non-homogeneous differential equation. Look at it. We have d squared y or dx squared. That's your second order derivative plus your first order derivative minus 2y equals e exponent x, your exponential plus a quadratic terms 3x squared minus 1. When you look at it, you're looking at this part right over here. You have an exponential and then you have the quadratic terms. From here, you will have your complementary function come about. From here, you'll have a particular integral and here another one. You'll have two particular integrals and a complementary function. All of these will combine to give you your general solution. And what will that general solution be? Let's find out. Let's start here with the complementary function. Look right here at the top. I have this y double prime plus y single prime minus 2y equals 0 because you're computing the complementary function as if you were dealing with a homogeneous differential equation where your function is equal to 0. Here your function is equal to exponential and a quadratic term. Now look over here. Your first order derivative with respect to e exponent rx is going to be r e rx. Then your second order is r squared e to the rx. These are the substitutions you make for the places that you see. You'll have here r squared e to the rx plus r e to the rx minus 2 e to the rx is equal to 0. You can eliminate these exponential terms because you could isolate them, push on the other side, they would divide by 0 and go away. You in essence have r squared plus r minus 2 equals 0. Factor this out. You have here r minus 1 and you have r plus 2, which means r is equal to 1 comma minus 2, or you can say minus 2 comma 1. It depends on how you want to itemize it. I'm going here with this. So when I'm looking at that, my complementary function based on the template where you have two real solutions, distinct separate real solutions, will be y is equal to a e exponent x and then another constant plus b e exponent minus 2x. Here are my solutions 1 and minus 2. As you can see, 1 and minus 2. You could flip those around. You could say a e exponent minus 2x plus b e exponent x. It doesn't matter, but the complementary function has been completed. Now focus here on the first particular integral we'll determine right here, pi1 and pi2. This is to do with the exponential. Now look right over here. When you're looking at an exponential term, you have to use a certain template and it would be ce exponent x. But look right here, this looks, ce exponent x looks very much like ae exponent x, which you're seeing right over here. When you are seeing a template that you're about to use for your particular integral, it is exactly what you see in your complementary function. You will have a problem down the road. Therefore, you must make a modification. Your modification that you will do is this cx e exponent x. You will not use this, but you will use this. And then you will run that through your derivative techniques and your particular integral determination. Again, when you have something like this, your template mirroring something you have over here, you must make this modification, bring in an x, and that is what we will do. I know now my template will be c, a constant x e exponent x. Your first order derivative with respect to this is going to be what? Do the product rule for these. You'll have e exponent x plus x e exponent x. You can do this in your head because it's not hard. Open everything up, you'll have c e exponent x plus c x e exponent x. You'll do your next order derivative, do the derivative of this. This part right here is easy, it'll be c e exponent x plus. Now do the product rule over here. I'll bring the constant outside and I'll do exactly what I had over here. I'll have e exponent x plus x e exponent x. When I open up everything and I combine everything, I'll have over here a 2c e exponent x. And then I'll have a plus cx e exponent x. These are the items now which will come right over here in terms of substitution. I know my second order is this. So I'll bring it in. I have a 2c e exponent x plus cx e exponent x plus this term right here, your first order derivative, which is right here, plus c e exponent x plus cx e exponent x minus 2y. Y is all of this, so you'll do minus 2 cx e exponent x is equal to e exponent x, as you see right here. Now look, something will cancel out. If you didn't do this minor modification right here where you bring in the x, this particular x that you're seeing, what would have happened here is you would have had 0 is equal to e exponent x, and you would not be able to determine the value, and you would see there would be an error and you would stop over there. But by bringing in this x, you can actually compute your answer, your particular integral. You have this combining with this, cancelling out of that, because that's 2cx and that's minus 2cx. They cancel out. I have these things remaining, which is 3c e exponent x is equal to e exponent x. When you cancel out the exponential terms, it's equal to a 1. Here I know c is equal to 1 over 3. When I bring everything right over here in this, then I know my template over here is going to be what? It's going to be my particular integral for this right here. I'll put it for you, will be 1 over 3 x e exponent x. Here's my particular integral. We'll work on it at the end. My complementary function determined early on is right here. All we have to do is determine the second particular integral, and then we are done. When you look at that second item, the second function, you have a quadratic term, 3x squared minus 1. You know, when you're looking at quadratics, you're looking here at your template, cx squared plus dx plus e. That's what you have. Now you have to do the first order derivative of this, which is what? 2cx plus d. You can do the second order derivative, which is a 2c. These are the items you'll bring here, and then they'll equal to your quadratic terms. My second order derivative here is a 2c. Note again that this right here is equal to y double prime, and this right here is equal to y single prime, but you know this. Here you're looking at the official terminology as you can see it. I have a 2c coming over here. I have my first order derivative coming here, which is a plus 2cx plus d. Then I have my minus 2y, which is minus 2 times all of this. All of this will give you your systems of linear equations. You'll have a minus 2cx squared minus 2dx minus 2e is equal to your quadratic terms. And let's bring them in. 3x squared plus 0x minus 1. I have now all the terms accounted for. I'm erasing this part right over here because you don't need to see it. We'll keep the template right here. We will need it. Look at your quadratic terms. My quadratic terms are the ones with the x squared. I have a minus 2cx squared is equal to 3x squared, and you know from here clearly c is equal to minus 3 over 2. Your quadratic coefficient has been solved. Now look at your linear terms, your x terms, which are what I'm marking for you right here. I have a 2c, but I know c is a minus 3 over 2. 2 times minus 3 over 2 is a minus 3. Then I have a minus 2d is equal to a 0. Solve for d. When you solve for d, what do you get? You have here a minus 3 over 2 again. Solve it out, it's easy, minus 3 over 2. Now look at your constant terms where you have no variable. Your constant terms are this, 2c and d, a minus 2e and a minus 1. Bring in your items. I have a 2c. 2 times minus 3 over 2 is a minus 3. Then I have a plus d, which is a minus 3 over 2. Then I have a minus 2e is equal to a minus 1. Solve for e. When you push these two terms on the other side, what do you have? You have a minus 1 plus. This is a 3 and a 1.5, which is a 4.5, which you know is going to be a 9 over 2, which is a 4.5. Remember, 3 plus 1.5 is a 4.5. This is minus. It goes on the other side, it becomes positive. When you're taking a full out of a 9 over 2, you know you're getting a 7 over 2. But 7 over 2 is equal to minus 2e. And then you know e is equal to minus 7 over 4. And we'll bring that here. E is equal to minus 7 over 4. Nothing but arithmetic, and you can easily do this on your own. Let's write it again. Clearly minus 7 over 4. We have everything we need now to make our next template, our particular integral solution, which is this. Your any solution is always y equals. Your complementary function y equals, your this y equals, your this y equals, but you can designate them separately. You can say y complementary function, then you can say y particular integral 1, then you can say y particular integral 2. This right here is our particular integral 2. Let's put it down. It will be y is equal to all of these items coming into place of c, d, and e. You'll have a minus 3 over 2x squared minus 3 over 2x minus 7 over 4. If you want to combine these under a common denominator, you can. You can even say you have minus 3x squared minus 3x over 2 minus 7 over 4. This way you've combined it and it looks a little better. And we'll bring our general solution now for you. Our general solution, as you can see over here, is complementary function plus that. And let's do it. Our general solution, we'll say y gsy general solution is equal to our complementary function. You have it over there, a e exponent x plus b e exponent minus 2x. It's a second order differential equation, so I have two constants over here, and that's good. Our one particular integral, which is this 1 over 3x e to the x, and we'll bring the next item over here. I'll bring it in this form right here. Even though I said I'll do this form because I think it'll be better to have everything separate. minus 3 over 2 x squared minus 3 over 2 x minus 7 over 4. Here is our solution. My general solution is equal to a complementary function, a particular integral and another particular integral. All of it should be correct. And this right here is the end of this question. Have a good day. Thank you.